All right, let's try number 4. Number 4 says, for a reaction with a second order rate constant, the correct unit for K is molarity times time to the minus 1, true or false. Well, for a reaction whose rate is second order, we could write the expression as being equal to K times A raised to the power of 2. This would be a reaction, A goes to product, second order. And so therefore I could write my rate law expression that way. What are my units of K is basically what this question is testing. I know that my units of rate must be, for any reaction that we write, must be concentration, so moles per liter per unit time. And let's choose our time unit as a second. So it's mole per liter per second. And this is equal to my units of K, which in this question are basically my unknown. So I'm just going to shade this little box in as my unknown, times concentration squared. So moles squared over liters squared, because that would be concentration to the power of 2. And then isolating then for my unknown units, I have moles per liter per second, and that would be divided by moles squared per liter squared. And so that's the same thing as multiplying by the reciprocal, liters squared, moles squared. Cancel, 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 cancel. And I'm left then with the units of my second order reaction rate constant K as being equal to liters over mole times seconds. And in terms of molarity, I can tidy up this unit a little bit. This is not molarity, but it's molarity to the minus 1. So that would be m to the minus 1 times seconds to the minus 1. Now, if you look at what the possible answers are for number 4, well, it's true or false, but the unit it says is molarity times time to the minus 1, and that's false because it's molarity to the minus 1 time unit to the minus 1, which we've assigned as seconds. And just before we finish this question, I just want to point out to you that this would be also true for any second order reaction. We could have, for example, A plus B goes second order to product, because my rate could also be written K times A to the first, B to the first, and the overall order 1 plus 1 is 2, and that's basically still giving me concentration squared on this side, but we just did it for the simplest case. So any second order reaction rate constant K will have units of molarity to the minus 1, seconds to the minus 1, and we showed that for the simplest case. Okay, so that's number 4. Let's try number 5. Number 5 says that the energy of activation has no effect on reaction rate. The energy of activation, 5. The energy of activation is what we symbolize as EA. And it says it has no effect on the reaction rate. Well, one of the equations that you're given on the exam is called the Arrhenius equation. And the Arrhenius equation is one that relates the reaction rate constant to, A for Arrhenius, e to the minus EA over RT. So we see that it's not so much the rate that depends on the temperature. We know that it does, but the reason why it does is because it's the K value that depends on the temperature, and temperature is in the exponent. So if you increase the temperature a little bit, the rate goes up a lot. And so number 5 says the energy of activation has no effect on the reaction rate. That is false, because the larger the activation energy, the bigger the barrier. You may have seen this in another textbook or in ours, the energy profile versus the extent of reaction. You may have seen this. I won't ask you to reproduce this for the exam, but where you have your reactants and then you have your products over here, your reactants have to combine and their energy has to surpass this difference here, which is your activation energy. So the bigger the activation energy barrier, the slower your reaction rate because they're just not making it over the bump. And this is where we bring in a catalyst, because a catalyst will lower the activation energy barrier and therefore increase the rate. So number 5 is false, because in fact, the energy of activation does have a big effect on reaction rate. And finally, let's do number 6 in this single clip. Number 6 says that the temperature has no effect on reaction rate. And I think it's almost intuitive that this is for sure false, but we'll just demonstrate that. Again, the Arrhenius equation is that the reaction rate constant is equal to this pre-exponent guy times a base e to the minus activation energy over RT. And we see that temperature has a big influence on the reaction rate constant. And so number 6 is false. Okay. In fact, we can go ahead and do number 7 as well, because it also has to do with the Arrhenius equation. And in number 7, they're talking about the natural log version of this. And so if I take the log of both sides, the natural log, I get the ln of k is equal to the ln of A minus activation energy over RT. And that's the natural log form of this equation. And number 7 says that the symbol A denotes the initial concentration of A. Is that true or false? Well, I can see that this all has to be apples, apples, and apples. And by that I mean that whatever units this has, this also has to have. So the units of K are the same as the units of A, and therefore A does not denote a concentration. A has the same units as K. And in fact, once we take the ln of it, we take the ln of just the number without its units. But in question 7, it says that A denotes the initial concentration of A, and that's false. It denotes what's called the Arrhenius parameter. And an Arrhenius parameter, as we can see probably better from this form of the equation, A has the same units as K. And so, getting back to the question, number 7 then would be false. All right. And I think we can actually do number 8 because we talked about it. I can find room on my paper that's not been used up. So let's look at number 8. 8 says adding a catalyst lowers the activation energy of a reaction. That's absolutely true. Very quickly, the reason why is, again, if I look at my energy profile, specifically potential energy, I start off with my reactants. They combine, they surpass an activation energy barrier, and in this case, they go to higher energy products. So this would be an endothermic reaction. This difference here is my activation energy. When I add a catalyst, just to draw a different path, what a catalyst does is it actually offers a lower activation energy barrier. It lowers it. And so when we use a catalyst, the activation energy decreases to this amount in this case. And so number 8 says adding a catalyst lowers the activation energy of a reaction. That's absolutely true. We've written it already. And there you go. Okay, let's stop here.